All right, so here's an example of a series circuit breakdown. I'm going to give you some values and some empty pieces, and our goal is to fill in all the blanks. So here's an example, and we'll call this a series circuit breakdown. And we're going to be doing this in this unit, breaking down circuits. So now we have the same circuit. I'm going to redraw the circuit we just had. There's our power supply. I'm going to give 3 resistors again. All right, and then I'm going to close off my circuit. I'm going to give you some values. So this circuit has a supply voltage of 10 volts. There's some total current coming out of that battery, I total, that we don't know. So I'm going to leave a line here. We do know all 3 resistor values. R1 is equal to 2 ohms. R2 is equal to 5 ohms. And R3 is equal to 13 ohms. So again, those are resistance values. If you think of these as toll booths, more resistance is like a toll booth that is going to take longer to pass through. So you might have, there's 2 kinds of easy pass lanes. If you get on the blue route, right, and you go through that Conshohocken area, you see that there's that lane where you don't have to slow down at all. You can go flying through there at 60 miles an hour. That's like your 2 ohm resistor. Then you have ones with no gate easy pass. They're pretty fast, but you got to slow down to 20. So maybe that's your 5 ohm. And then you got ones with a gate, and maybe it's still easy pass, but you got to slow down to a stop for that gate to open. That would be like your 13 ohm, right? And so those are 3 kinds of toll booths that you might have to pass through. In this case, you have to pass through all 3. So these are at different locations along that highway that you're going to hit that highway. You're going to eventually go through 3 toll plazas in succession, in order. So you effectively get slowed down by all 3. Because you have to pass through all 3. They're in series. So that's how I like to think of series is as toll plazas, slowing down the flow of traffic. All right, so what we want to know if we're going to break down the circuit is not only the total current, but I want to know the voltage drop and the current through each resistor as well. So I'm going to write V2 and I2. So breaking down the circuit, we're going to find the voltage drops, which are these voltage. We call those a voltage drop across those resistors. And I want to know the current through each resistor. All right, and so we have enough information actually to fill in all those blanks and break down this circuit. And the first thing we're going to do, and usually this is something you can do for most circuits because you're going to typically know the resistance. Sometimes you don't, and it becomes a little bit of a puzzle. But the first step is we're going to find the equivalent resistance of our circuit. And because we're in series, we know that that equivalent resistance of this circuit is just going to be the addition of all of those resistor values. Oh, my OneNote just pooped on me here. Let me close this. I'll open it back up. We've seen this happen before. The pen was acting kind of funny. All right, we're back. All right, so we're going to basically add all 3 resistors. So plus R3. And so all I have to do is take R1, which is 2 ohms, plus R2, which is 5 ohms, plus R3, which is 13, right? And you get a total of 20 ohms. Right, so I know that my equivalent resistance of my circuit is equal to 20 ohms. And usually we'll write that in here as well on my diagram, what REQ is. Right, and so now we've just found that to be 20 ohms. Right, so if I'm starting on this journey in my car, I can pass through 3 toll booths, or I can pass through 1 equivalent toll booth that would slow me down and take me, let's say, 20 seconds to pass through versus these other ones. All right? And so that's going to dictate the flow. All right, so now that I know that I'm eventually going to pass through 20 seconds of toll booth delay, well, that's going to dictate how long it will take me to get from one end to the other, and therefore affect my overall speed through that circuit. And so this is where we can now figure out our total current passing through. And so we can redraw our simplified circuit. So now that I know my equivalent resistance, I've effectively can redraw this circuit as a voltage supply, one equivalent resistance, and take it back through. And this is now 20 ohms. We know this is 10 volts, and so we can actually calculate I total. And so we can find I total. I total is always going to be equal to the supply voltage over that equivalent resistance. V equals IR, or I equals V over R. And so if I take 10 volts, the supply, over that 20 ohms, I get an equivalent resistance of 1/2 of an amp. And so I can go back into my table now, and I now know that I total is 1/2 of an amp, right? Or 500 milliamps. There is 1/2 of a coulomb passing through every point every second. And because we're in series, I now know that each of these sees 1/2 an amp. So I can write the 0.5 amps in for each of these. And now I'm a step closer to being able to actually find the voltage drop across each of these. All right, and so now that I know what the current is and what the resistance is, I can go in here and I can calculate the individual voltage drops. And again, it's Ohm's law. Right, so the voltage drop across 1, V equals IR, is going to be the current across 1 times the resistance of 1. That current is 0.5 amps. The first resistance is 2 ohms, and so I get 1 volt of drop. For V2, it's going to be 0.5 amps times 5 ohms, and I get 2.5 volts. And the voltage across the third resistor is going to be 1/2 an amp times 13 ohms, which is 6.5 volts. Right? And lo and behold, if I were to add those up, they should add up to the total voltage, which is 10 volts, which is my supply. So I know that everything checks out. I know the voltage drops across each of these. So the first one's got a 1 volt drop. This one's got a 2.5 volt drop. And this one's got a 6.5 volt drop. And now I've broken down every circuit. If I were to take that voltmeter and put the probes on either side of those resistors, those are the voltage values you would get. And over the course of that circuit, I have 10 volts of electric potential. I drop 1 volt on the first one, not much because it's low resistance. Drop another 2.5 over the second, and drop the most over that 13. Notice we talked about it being proportional to the amount of resistance. More voltage drop for more resistance in that circuit. At the end of the day, I drop all of my voltage in that circuit. All 10 volts will always get dropped in any circuit loop.